this project, we developed an AI-based air traffic controller using reinforcement learning. The goal of this AI is to guide aircraft to their destinations while avoiding collisions and creating efficient flight paths. Instead of programming fixed rules, the AI learns its own control strategy through experience. To train the AI, we first made a custom aircraft simulation environment. So this is the plane class, which makes the plane object that has things like its position and its speed, angle, and altitude. The way we let the autopilot move this aircraft is by having an autopilot input, which sets the target speed, heading, or altitude to the airplane, and the airplane slowly moves uh, towards those targets using a PID controller, which uses calculus for smooth movements. And then we have the plane sim class, which um, has a list of planes in airports and lets them makes them run all at once, each step in the environment. The So the AI doesn't directly move the aircraft. Instead, it acts like an air traffic controller. Because of the limitations of our limitations, we only tell the aircraft to move, change its heading, and not its speed or altitude. So um, the first environment we made, so we make the its step function makes an action, and the action is normalized from -1 to 1. So it's multiplied by 180 for the target heading. And then it lets the plane run for 30 seconds, or in this one it's 60 seconds. And then it returns the rewards and observations. So, yeah. The aircraft simulator then this creates a realistic control loop where the AI must predict how its decisions will affect the aircraft in the future. So in our final two uh, plane environments, we have the single plane environment, which has 8 total observations, which is the uh, delta x and delta y from the airport, the speed, the sine of the heading, and the cosine of the heading to make sure the isn't the angle doesn't affect the results, because the angle is wrapped around from 0 to 360, and those two values are very different. And then we have the angle error from the plane to the airport, the distance and the time left it has to get to the airport. So how we train it is that um, we use RLlib, which is a library for reinforcement learning, and we put the environment into RLlib, and then we use their own PPO configuration, which is reinforcement learning model. And then we can change stuff like the neural network used in PPO, like for example, we can change the batch size to 4096, which means it uh, trains the model every 4096 environment steps and trains the model for 10 epochs. The model also has two hidden layers of 128 neurons each, and its activation function is tanh. Let me change the It's gonna take a second to load here. So while it's loading, I'll show you the videos that we have of our training. So in the first iteration, we record a video, and it shows that the plane is just moving in a random direction, not towards the airport. And then this is the 8,000th epoch, and it shows that the plane is effectively moving towards the airport in about the shortest time it can. So this is saving the first videos, and then it starts training. Yeah, so every iteration, which is 10 epochs and 4,000 environment steps, we get values like these for our uh, to debug the model. And it shows at the start the reward is very low, but later yeah, at the start the reward is very low, and these other values yeah, so we can actually see the the some more metrics for training. So this is some metrics for a one plane training log, and it shows that the uh, at around 800 we changed the rewards so that the plane can train better. So that's why it changes. But from here, the entropy is going lower, which means the model is being more predictive. Here, again, we changed that at 800. So the episode length is going down because um, the airplane is reaching the airport faster. And yeah, the model rapidly improved from like 0 to 200, and then it kind of plateaued around these parts. So after we got that, we trained the second model, which is for multiple planes, and then it's pretty much all the same, except we transfer the weights by moving all the old weights into and there's a problem with this because the one plane model has a different observation space than the multiple plane model. So we had to transfer the weights from the one plane model. Okay, so the observation space difference means that the neural network takes a different amount of inputs. So we had to transfer the one plane model's observation space and weights into the two plane model and fill the extra weights that the multiplane model makes. So this is how we did it. And also, so the training is pretty much the same for the two plane model. Uh, it uses pretty much the same configuration for training, and these are the results. So this is the first iteration. It's pretty much just crashing, and then here's after 3,000 epochs. Hold on, not that one. It's yeah, it should be this one. So this is after 3,000 epochs. This is the result we have, and we're still training it. Yeah. And how we save these videos is that we run it we run it 5 episodes each time, and the RGB sim RGB saves the videos through NumPy file, and then by rendering it and then saving each image of each render. In each image is 1 second, so it saves a numpy file, and we save it to this folder, and then we just render it from here. Overall, this project demonstrates how reinforcement learning can be applied to air traffic control by allowing an AI agent to learn through simulation. It can discover effective strategies without requiring every situation to be manually programmed. Future improvements could include supporting larger number of aircraft, adding more realistic aviation constraints, and improving flight efficiency by reducing unnecessary flight adjustments. Thank you for listening.